Life on Earth occupies only a thin film across a single planet, yet the universe stretches far beyond anything the human eye can grasp. Billions of stars fill the Milky Way. Beyond them lie billions of galaxies, each one with its own habitats, its own temperatures, and its own chemical landscapes. Somewhere within this expanse, conditions may have shaped molecules that organized themselves into living systems. If life formed here, it may have formed elsewhere. The challenge is finding it. Human eyes alone cannot search these distances. The light is too faint. The signals are too subtle. The worlds we hope to study are hidden in glare dust and vast layers of darkness. To overcome this, we have built machines to work as our extended senses. These machines hover above clouds, land on distant surfaces, or drift through deep space. Some analyze rock, some measure vapor, some read the fingerprints of gases carried through the atmospheres of faraway planets. Others listen to faint radio patterns that move through the galaxy. Our search moves along three fronts. The first lies within our own solar system, where rovers and orbiters explore environments shaped by ancient oceans, buried ice and active chemistry. The second front reaches outward toward exoplanets, where telescopes search for worlds that orbit distant suns. The third front listens for signals that might reveal the presence of advanced technology somewhere in the galaxy. These efforts work together. They form a network in which different machines collect different pieces of the same puzzle. Across deserts, ice fields, and oceans on Earth, people monitor these machines as they relay data through the vacuum of space. A rover's drill samples red dust on Mars. A probe detects water grains rising from a moon hidden beneath a crust of ice. A telescope records how a distant star dims by a fraction of a percent as a planet passes in front of it. Each measurement contains a trace of possibility. Each instrument extends the reach of the human species toward answers we could never obtain alone. If life exists beyond Earth, the first evidence may not come from a human footprint or a photograph. It may appear as a set of spectral lines, a ratio of molecules, or a pattern of radio frequencies that stands out against natural noise. And if that moment arrives, it will be delivered by one of the machines we've placed among the stars. The search for life began long before any spacecraft left the ground. Early astronomers used small glass lenses to observe the night sky. These instruments revealed moons around Jupiter, shadows across the surface of Mars, and clusters of stars that stretched farther than anyone imagined. Yet these sights were limited by turbulence in the atmosphere and by the narrow range of visible light. They could show beauty, but they could not show the chemistry or conditions necessary for life. As telescopes grew larger, mirrors replaced lenses. Metal and glass collected more light than any human eye could perceive. Observatories climbed mountains to escape layers of thick air. Detectors became more sensitive, able to record faint glows that came from clouds of gas, or young stars forming in dust-filled regions. Still a question remained. To find life, one must detect water, methane, oxygen, organics, and the minerals that shape planetary surfaces. These signals hide in wavelengths the atmosphere absorbs or distorts. A telescope on Earth can only see part of the story. The arrival of space-based observatories changed everything. Freed from clouds and air, telescopes could observe the universe in ultraviolet, infrared, and radio wavelengths that never reach the ground. The Hubble Space Telescope became the most famous of these machines. Its position above Earth allowed it to record star-forming regions, distant galaxies, and the structure of nebulas with clarity that transformed astronomy. By resolving fine detail, Hubble confirmed that many stars form in clusters surrounded by disks of gas and dust. These disks would later become essential to understanding how planets arise. Yet even with these advances, the instruments of that era were not built specifically to search for life. They could show where stars grew, how galaxies evolved, and how the universe expanded. They could not identify the chemical markers that indicate biology. That required technology capable of reading the makeup of atmospheres and surfaces across light years. It required tools designed not only to look outward, but to analyze and interpret the faintest patterns in light. These needs shaped the next generation of machines. Engineers began to design instruments that could split starlight into precise spectra and detect subtle dips in brightness as planets crossed in front of their stars. They worked on sensors that could recognize the signature of water vapor, carbon dioxide, and methane in the tiny fraction of light that passes through an exoplanet's atmosphere. The path toward finding life wouldn't rely on a single telescope. It would require a global shift in how humanity observes the universe. The first steps toward that shift began not around distant suns, but in our own solar system. Rovers, orbiters, and landers would become the pioneers in reading the history of planetary surfaces. Their discoveries would guide the questions that larger telescopes would later ask. The machines that searched the ground prepared the way for the machines that now search the sky. Before searching the galaxy, scientists turned their attention to the worlds within reach. The solar system offered accessible environments shaped by water, rock ice, and sunlight. Each world carried records of chemical reactions that had unfolded over billions of years. Some preserved ancient oceans, others hid reserves of frozen water or displayed signs of heating below their surfaces. If life ever formed close to home, even at a microbial scale, its traces might remain in minerals or trapped within layers of ice. To begin this investigation, engineers built orbiters that could map planetary surfaces with high-resolution cameras and spectrometers. These machines studied craters, valleys, and polar caps from above. They measured the composition of rocks and minerals by analyzing the light reflected from them. They looked for signatures of past water such as hydrated salts, clay deposits, or layered sediment. Each observation helped define targets for later missions that would land on the ground. Landers and rovers offered a level of detail impossible from orbit. They carried drills, microscopes, chemical analyzers, and environmental sensors. They could move across landscapes shaped by ancient rivers or volcanic activity. They could study the texture of soil, identify minerals formed in water, and detect organic compounds that may have survived for millions of years. By comparing these findings with what is known from Earth, scientists could reconstruct the environmental history of these worlds. Mars became the primary destination for these tools. Its dry valleys and layered canyons resemble landscapes carved by flowing water. Orbital imagery revealed channels, delta shapes, and minerals that form in wet conditions. Rovers could explore these areas directly and examine rocks that formed when conditions were warmer and wetter. They could determine whether the planet once had environments stable enough for chemistry associated with biology. The search expanded beyond Mars as evidence for hidden oceans appeared on icy moons. Europa, a moon of Jupiter, displayed cracks and ridges that suggested a deep ocean below a shell of ice. Enceladus, a moon of Saturn, released plumes of vapor and ice particles into space. These discoveries revealed that some moons might host liquid water beneath their surfaces warmed by tidal forces rather than sunlight. They opened a new frontier in the search for life, one based on environments far different from the deserts and plains of Mars. The solar system became more than a collection of planets and moons. It became a set of natural laboratories, each with its own path through geological and chemical evolution. By studying these worlds, scientists learned which conditions favor organic molecules, and which environments can preserve evidence for long periods. These lessons shaped the strategies for searching more distant planets. They demonstrated that the ingredients for life may arise wherever water energy and stable chemistry coexist. Mars became the central stage for machines built to search for traces of ancient life. Its thin atmosphere, cold temperatures, and dry soil make present-day biology unlikely, yet its past tells a different story. Orbital images show river channels that once carried flowing water. Minerals on the surface formed only in wet environments. Layered rocks mark locations where sediment settled in calm pools. These clues guided engineers to design rovers capable of reading the geological memory preserved in Martian stone. Spirit and Opportunity began this exploration. They landed in regions shaped by water and carried instruments to identify minerals associated with ancient lakes and hydrothermal activity. Their cameras revealed fine layering within rocks. Their spectrometers detected hematite spheres formed in wet conditions. They showed that liquid water had interacted with the soil across wide areas of the planet. These findings confirmed Mars once hosted environments that could have supported microbes. Curiosity advanced the search with tools designed for deeper analysis. It carried a drill that could collect powdered samples from inside rocks. It delivered these samples to onboard laboratories that heated them to release gases for chemical identification. Through this process, Curiosity detected organic molecules that had survived for billions of years. It also measured variations in methane concentration in the atmosphere. While not direct evidence of life, these results pointed toward complex chemistry that required further study. Perseverance expanded the mission with a new capability. Instead of only analysing samples on site, it collected rock cores and sealed them in protective tubes. These cores will be returned to Earth by future missions where laboratory instruments can examine them with precision, far beyond what a rover can carry. The chosen landing site, Jezero Crater, contains a preserved river delta. Deltas on Earth trap sediments that can hold biological signatures. If Mars once hosted microbial ecosystems, this region offers one of the strongest chances to preserve their traces. Each rover carries an array of sensors tailored to detect potential biosignatures. Cameras record textures that resemble stromatolite-like patterns. Microscopes look for organic-rich layers. Spectrometers search for molecules that form in environments connected to life. These instruments do not search for living organisms. They search for the imprints ancient organisms might have left behind. They focus on patterns in minerals, isotopes, and organics that reveal past conditions rather than present activity. The work of these rovers established a foundation for the broader search for life. They demonstrated how machines can operate autonomously on distant surfaces, adapt to complex terrain, and perform laboratory-level tests in harsh environments. Their successes prepared the way for missions that would explore worlds where liquid water exists today. Not only in the distant past, those missions would target the icy moons where oceans lie hidden beneath thick shells of frozen crust. As rovers searched ancient landscapes on Mars, another frontier emerged in the outer solar system. Several icy moons showed signs of liquid water beneath their frozen surfaces. These worlds orbit far from the Sun, yet internal heating created environments where liquid water could remain stable for millions of years. Such conditions raised a compelling question. Could life arise in an ocean sealed beneath ice, warmed not by sunlight but by tides and chemical reactions deep below? Europa, a moon of Jupiter, became one of the strongest candidates. Its surface is a bright shell of fractured ice marked by long lines and broad ridges. These features suggest the ice shifts and breaks as the ocean below expands and contracts. Magnetic measurements indicate a conductive layer beneath the crust consistent with a global saltwater ocean. Where the ice thins, upwelling from below may bring chemicals from the ocean floor to the surface. These exchanges could deliver nutrients that sustain biological activity in darkness. Enceladus, a moon of Saturn, revealed even more direct evidence. Spacecraft flying past its south pole observed towering plumes of water vapor and ice grains erupting into space. Instruments sampled the particles and detected organic salts and molecules associated with hydrothermal vents. These findings point to interactions between rock and water at the bottom of a warm ocean. On Earth, hydrothermal vents host thriving ecosystems powered by chemical energy rather than sunlight. If similar chemistry operates on Enceladus, microbes could survive within its dark waters. To investigate these oceans, engineers designed orbiters capable of mapping the thickness of ice-tracking heat flow and analysing the composition of plume particles. The upcoming Europa Clipper mission will fly repeated passes above the Moon using radar to probe the ice shell and spectrometers to identify surface chemistry. A separate mission known as JUICE will study icy moons around Jupiter and measure their magnetic signatures. These machines will guide future efforts to reach beneath the ice. Concepts for the next generation of explorers include landers that can melt through ice, robotic submarines that can operate in low light, and autonomous drones that can navigate beneath frozen shells. These machines would search for gradients in temperature, the distribution of organic molecules, and the presence of sediments that form in hydrothermal environments. They would examine conditions that resemble the deepest ecosystems on Earth. The challenge is immense. The distance is great. The ice is thick. Yet the prize is significant. An active ocean sustained for billions of years offers one of the strongest natural laboratories for life. The discovery of these hidden oceans transformed the search for life. It expanded the range of environments considered habitable. It showed that sunlight is not required for biology to emerge. It revealed that chemical energy and liquid water can coexist even in distant frozen regions. These insights prepared scientists to look outward toward planets that orbit other stars. The next frontier lay not within our own system, but across the vast distances that separate the Sun from the nearest stellar neighbours. While machines explored deserts and icy shells in the solar system, another revolution unfolded in deep space astronomy. Scientists realized that most stars host planets. These planets cannot be seen directly with ordinary telescopes because the glare of their parent stars hides them from view. Yet the light of a star carries subtle signs that reveal the presence of worlds orbiting it. Detecting these signs required instruments with precision far greater than anything used before. The first breakthrough came from the transit method. When a planet passes in front of its star, the star dims by a small amount. The change is tiny, often less than 1%, but it is measurable with sensitive detectors. Each transit provides information about the planet's size and orbit. Repeated transits reveal the period of rotation and the shape of the orbit. Space telescopes such as Kepler used this technique to identify thousands of planets, establishing that the galaxy is filled with diverse worlds. Some planets are larger than Jupiter, others are smaller than Earth. Some orbit close enough to their stars to complete a full rotation in days. Others circle far away through cold outer regions. By studying these variations, scientists built a new understanding of planetary systems. They found worlds covered by thick clouds, planets with scorching temperatures, and planets with densities similar to rock or ice. The discovery of these systems opened the possibility that planets similar to Earth might also exist. The next advance came from missions like TESS, which scan broad sections of the sky to find planets around bright nearby stars. These targets are ideal for follow-up studies because their light is strong enough for detailed analysis. Large ground-based observatories complement these searches with radial velocity measurements. These instruments detect the slight wobble of a star as a planet pulls on it. This technique provides information about a planet's mass. Together, transit data and radial velocity data allow scientists to estimate density and infer whether a planet is rocky, icy, or gaseous. With these tools, researchers identified a group of planets located in the habitable zones of their stars. The habitable zone is the region where temperatures allow liquid water to exist on the surface. Planets in this region are prime targets for further study, yet detecting them is only the first step. To search for life, scientists must analyze the atmospheres of these worlds. This requires instruments capable of separating starlight into detailed spectra and measuring the faint imprint of molecules as light passes through a planet's atmosphere. These challenges prepared the stage for the James Webb Space Telescope, which became the most powerful tool for studying exoplanets. Webb could observe stars in infrared light and detect the chemical fingerprints carried through the atmospheres of distant worlds. It opened a path toward identifying biosignatures on planets that orbit stars trillions of kilometers away. The search for life had expanded beyond Mars and icy moons. It now reached across light years. The James Webb Space Telescope transformed the search for life into a precise study of distant atmospheres. Unlike earlier telescopes, Webb operates in infrared wavelengths that reveal heat dust and molecular signatures hidden from visible light. Its giant mirror collects faint photons that have travelled for years through interstellar space. Each photon carries information about the chemistry and structure of the world it touched before reaching the telescope. Reading these signals requires extreme sensitivity and stability, which Webb achieves at its orbit around the second Lagrange point. When a planet moves across the face of its star, some of the starlight filters through the planet's atmosphere. Molecules in that atmosphere absorb light at specific wavelengths. Webb splits the light into a spectrum and measures these tiny reductions. The pattern of missing wavelengths acts as a molecular fingerprint. Water vapor, methane, carbon dioxide, and other gases each leave distinct marks. By comparing observed patterns with models, scientists can determine which molecules are present and in what quantities. Webb has already demonstrated this capability by detecting water vapor in the atmospheres of several exoplanets. It has measured clouds, haze, and thermal structure on worlds far larger than Earth. It has also observed carbon-bearing molecules on smaller planets that orbit close to their stars. These findings do not confirm life. They reveal environments shaped by chemistry and temperature. They show which planets have the right conditions for liquid water or for complex molecules to remain stable. They provide a short list of targets for future missions to study in greater detail. One of Webb's most important contributions lies in its ability to observe planets orbiting red dwarf stars. These stars are smaller and cooler than the Sun. Their habitable zones are closer in, which means planets transit more frequently. Frequent transits allow multiple observations that improve accuracy. Webb can measure atmospheric composition, cloud cover, and possible chemical imbalances. If life affects the chemistry of a planet, it may do so through the creation or removal of gases. Detecting such patterns requires repeated, precise measurements over time. Scientists remain cautious when interpreting these signatures. Many gases associated with biology can also form through volcanic activity. Photochemistry, or interactions between atmosphere and rock. A convincing biosignature must appear in combinations that are difficult to explain through non-biological processes. For example, large amounts of oxygen and methane together would suggest active production and rapid replenishment. Webb cannot confirm such patterns alone. It can identify candidate planets that show unusual chemistry. Those planets become targets for future telescopes with even more advanced instruments. Webb represents a shift in the nature of exploration. It does not land on surfaces or drill into rock. It studies worlds from a distance by examining the light that touches them. Its power comes from its ability to turn faint spectra into detailed environmental profiles. Through this method, the search for life has expanded from direct contact with nearby worlds to remote sensing across light years. The next wave of space telescopes will build on this foundation and push deeper into the atmospheres of planets that may resemble Earth. As telescopes examine the chemistry of distant atmospheres, another branch of the search focused on signals that might indicate advanced technology. Life that develops tools or communication systems could leave detectable traces across space. These traces, known as technosignatures, differ from natural emissions. They often appear as narrow signals concentrated at specific frequencies or as repeating patterns that stand out from the background. Instruments built to detect them must distinguish artificial order from the vast noise produced by stars, planets, and interstellar clouds. Large radio arrays became the primary machines for this task. These networks consist of dozens or even hundreds of antennas spread across wide regions. By combining their signals through digital processing, the arrays act as a single instrument with high sensitivity and resolution. They scan the sky for faint tones that remain stable in frequency and direction. They search for bursts that drift in ways consistent with planetary motion. They look for patterns that cannot be explained by natural processes such as pulsar emissions or cosmic microwave background fluctuations. Projects dedicated to this search examine billions of radio channels. Algorithms filter data in real time and flag potential signals for deeper review. Many detections turn out to be reflections from Earth-based transmitters. satellite interference, or natural astrophysical events. Each candidate must be rechecked through independent observations. No confirmed technosignature has been identified. Yet the capability of these machines grows rapidly as computing power increases and data pipelines become more efficient. Technosignatures extend beyond radio waves. Some missions search for laser pulses directed across interstellar space. Others analyze the brightness of stars to look for unusual dimming patterns that could indicate large structures orbiting a star. These searches rely on high-precision photometry. They examine variations in light curves that differ from the smooth shapes produced by planets. Although no artificial structures have been identified, the data from these surveys improves models of planetary systems and expands the catalogue of natural phenomena. Another possible technosignature lies in planetary atmospheres. If a civilization alters its environment at large-scale, pollutants or industrial gases may accumulate. These gases could leave spectral fingerprints detectable by future telescopes. Molecules such as nitrogen dioxide or chlorofluorocarbons do not occur naturally in high concentrations on lifeless worlds. Detecting them would require extremely sensitive instruments and careful analysis to exclude natural explanations. Webb has opened this field by demonstrating that atmospheric chemistry on small rocky planets can be studied even if current sensitivity remains below the threshold for such detection. The search for technosignatures pushes machines to their limits. It demands stability in frequency measurement, precision in photometry, and the ability to analyze massive streams of data. It also depends on coordination between observatories across the globe. A genuine signal must be confirmed by independent instruments operating at different locations and frequencies. Through this system, the search gains reliability while reducing the chance of false discoveries. Together with planetary spectroscopy and in situ exploration, technosignature searches form the third front in the quest to detect life. They highlight the possibility that biology might produce patterns recognizable across interstellar distances. While no evidence has been found, the machines built for this purpose continue to expand their reach, scanning the galaxy with growing sensitivity. As instruments grew more powerful, the challenge shifted from gathering data to understanding it. Telescopes recorded thousands of spectra, rovers generated millions of images. Radio arrays produced streams of signals that changed every millisecond. No team of scientists could inspect every detail. The search for life required a new type of machine, one that could recognize patterns hidden within vast volumes of information. This is where artificial intelligence entered the mission. Machine learning algorithms excel at detecting faint relationships. They can identify patterns that might escape the human eye. In exoplanet studies, these systems sort through light curves to find transits buried in noise. They locate shallow dips that reveal small planets. They correct distortions produced by star spots, instrumental drift, or cosmic rays. By automating these steps, AI allows scientists to focus on the most promising candidates while increasing the speed of discovery. Rovers on Mars rely on similar systems. Their cameras photograph rocks, dust, and layered sediments. The images are sent to Earth, where machine learning algorithms classify minerals, flag unusual textures, and highlight regions where water may have shaped the terrain. These models help mission teams choose drilling sites and guide rover movement across complex landscapes. They maximize the scientific return from every step, every sample, and every exposure. In radio astronomy, AI filters enormous amounts of data to identify potential technosignatures. It evaluates each signal through a set of criteria. It tracks frequency, drift shape, repetition, and direction. If a pattern resembles something artificial, the algorithm marks it for further inspection. These flagged events are then reviewed by scientists who separate interference from genuine anomalies. This human-machine partnership expands the reach of telescopes beyond what manual analysis could achieve. AI also plays a crucial role in atmospheric spectroscopy. When Webb delivers a spectrum, the dataset contains thousands of variables. Temperature, pressure, molecular absorption, and cloud properties interact in complex ways. Machine learning models compare observed spectra with millions of simulated ones. They estimate the most likely combinations of molecules. They search for outliers that might indicate new chemistry. This approach allows researchers to analyze atmospheres that would otherwise be too complicated for direct interpretation. Despite their power, these systems do not replace scientific judgment, they amplify it. Every conclusion still requires verification through repeated observations, alternate models, and independent measurements. I highlights what deserves attention. It does not decide what counts as evidence. The search for life demands caution because natural processes can mimic biological signatures. The role of AI is to uncover possibilities faster than traditional methods, not to claim discoveries. The integration of autonomous reasoning marks a turning point. Machines now gather data across the solar system, analyze signals from distant stars, and assist in the interpretation of planetary atmospheres. They extend both the senses and the thinking patterns of the human species. Through them, the search for life becomes more comprehensive and more precise. The next frontier lies with instruments that will push these capabilities even further, targeting planets that resemble Earth more closely than any explored so far. The tools that operate today offer only a glimpse of what future instruments may achieve. Engineers are designing machines that can isolate the light of an Earth-sized planet from the glare of its star. They are developing telescopes large enough to detect faint atmospheric signals that lie beyond Webb's reach. These concepts represent a new stage in exploration. They aim to observe planets not only as shadows in transit or as chemical spectra, but as full worlds with weather patterns, surface features, and long-term climate cycles. One key idea is the large segmented mirror telescope placed in deep space. Such a machine would gather far more light than current observatories. It would use coronagraphs to block starlight and expose the dim glow of orbiting planets. By analyzing reflected light, it could identify oceans, continents, and clouds. It could detect seasonal changes caused by vegetation or atmospheric chemistry. These observations require long exposures and extreme stability. They demand hardware that can maintain alignment within tiny tolerances while operating in the cold environment around the second Lagrange point. Another concept involves fleets of small spacecraft flying in coordinated formation. By synchronizing their positions, these spacecraft form an interferometer with a virtual mirror far larger than any single telescope could carry. This configuration allows scientists to resolve details that would otherwise be impossible. Formation flying requires precise navigation and communication. If achieved, it would create instruments capable of imaging planets with clarity that approaches direct photography. Such missions could reveal surface color variations, cloud belts, and thermal gradients. Within the solar system, new designs target the icy worlds that hide internal oceans. Engineers are developing landers that can drill or melt through thick ice. These machines would carry sensors to study the chemistry of water beneath the crust. Some concepts include robotic submarines that can travel through the dark ocean and map the seafloor. They would search for mineral deposits, hydrothermal vents, and chemical imbalances that hint at energy sources. If organic particles drift near the vents, the machines could analyze their structure and determine whether they form through geological or biological processes. Exploration near the Sun may also advance the search for life beyond Earth. Solar-powered spacecraft can operate for long periods and gather high-precision measurements of dust gas and interplanetary chemistry. Missions similar to Parker Solar Probe reveal how stellar winds interact with planetary atmospheres. By studying these processes around the Sun, scientists refine the models used to interpret exoplanet atmospheres. Improved models allow researchers to distinguish between signals produced by life and signals produced by natural chemical cycles. Ground-based observatories are evolving as well. Future instruments like extremely large optical telescopes will use adaptive mirrors to correct atmospheric distortion. They will capture faint spectra from exoplanets discovered by space telescopes. They will measure variations in atmospheric composition over time, providing data that complements orbital observations. With this combination of ground and space-based capability, the search for life will enter a phase of detailed environmental study. These proposed machines push the limits of engineering. They demand new materials, new methods of control, and new ways to coordinate systems across vast distances. Yet each concept is guided by clear scientific objectives. They aim to detect molecules in atmospheres, identify surface features, explore subsurface oceans, and measure chemical energy sources. They are designed to answer a simple question: if life exists beyond Earth, how can we detect its presence with confidence? If signs of life appear beyond Earth, the first evidence will likely be subtle. It may come from a pattern in a spectrum or from a chemical ratio preserved in a rock. It will not arrive as a clear image or a direct observation. It will appear as data that demands careful analysis and repeated confirmation. Scientists approach such possibilities with discipline. They know that nature produces complex signals that can resemble biological activity. A true discovery must be checked from every angle. One scenario involves atmospheric chemistry. If an exoplanet contains gases that react quickly with one another, such as oxygen and methane, maintaining both requires constant replenishment. On Earth, biology provides that replenishment. Detecting an imbalance on a distant world would raise questions, but it would not be proof. Models would need to exclude volcanic outgassing, photochemical reactions, and surface interactions that could imitate biological cycles. Only when all non-biological explanations are ruled out can a biological hypothesis gain strength. Another scenario involves direct sampling within the solar system. A lander that drills through ice or a submarine that explores an ocean could find complex organic molecules or structures that form through metabolic processes. Even then, the interpretation must be cautious. Organic molecules can arise naturally in many environments. A convincing biosignature would require patterns that indicate replication, chemical gradients that imply energy use, or isotopic ratios that match those produced by living systems on Earth. These measurements must be repeatable and supported by multiple instruments. Radio searches offer a different path. If a narrow, stable signal appears at a frequency unlikely to arise from natural processes, observatories around the world would study it. They would check whether the signal moves with the expected motion of a distant planet. They would look for variations consistent with rotation or orbit. They would ensure that the signal does not originate from Earth-based interference. Only after independent confirmation would the signal enter scientific debate as a candidate technosignature. Regardless of the method, every claim must survive a process of verification. This process involves repeated observation cross-checking with other telescopes and testing alternative explanations. Even once the data remains strong, the scientific community proceeds with caution. The announcement of life elsewhere would be one of the most significant moments in human history. It requires extraordinary evidence supported by independent investigations. The first sign of a life may therefore be quiet. It may appear as a small deviation in an atmospheric curve or as an unusual mineral deposit in an ancient rock. It may be a cluster of molecules that form in patterns unlikely to arise without metabolism. Machines would detect these patterns long before a human ever sees them. Through their sensors and instruments, humanity would gain the first hint that biology is not unique to Earth. This discovery would reshape the way we understand the universe and our place within it. Across the solar system and beyond it, machines continue to gather information that no human could reach alone. A rover studies the texture of Martian sediment beneath a cold, thin sky. An orbiter maps the ice shell of a distant moon and listens for signals rising from an ocean hidden in darkness. A telescope suspended far from Earth records the faint imprint of molecules carried through the atmosphere of a planet that circles another star. Radio arrays sweep the sky for patterns that might reveal technology beyond our own. Each instrument contributes a part of a wider picture. Together, these machines form a growing network. They operate across different wavelengths and under different conditions. Some examine dust and stone, some measure gases carried by winds, some interpret the subtle variations in light that pass through distant atmospheres. Others process signals that drift through interstellar space. Their data moves across antennas, relay stations, and fiber networks until it arrives in laboratories on Earth. From this continuous flow of measurements, scientists build models that describe how planets form, how atmospheres evolve, and how chemistry can support life. This search does not rely on a single mission or a single breakthrough. It advances through the combined effort of many instruments working across decades. Each rover, lander, orbiter, and telescope expands the frontier a little further. They show where water once flowed, where organic molecules persist, and where atmospheres reveal unexpected chemistry. They help determine which worlds deserve deeper exploration. They guide the design of future machines that will look with greater precision and reach even farther into the galaxy. Even if life remains undiscovered for now, the search itself reshapes our understanding of the universe. It reveals that planets are common. It shows that water and organic compounds appear in many environments. It demonstrates that conditions once thought rare exist in many forms. Through this knowledge, scientists refine the criteria for habitability and develop new strategies for finding life in places once overlooked. One day, a machine may detect a signal or a chemical imbalance that cannot be explained by natural processes. The data may come from a spectrum, a rock core, or a sequence of radio pulses. If that moment arrives, it will mark the first time humanity learns that biology exists beyond Earth. The discovery will emerge from the quiet work of instruments that explore regions no human has ever visited. For now, the search continues. The machines we've built travel through shadowed canyons, glide above frozen surfaces, and drift through deep space. They carry sensors tuned to faint signals. They operate in silence and send their findings home across long distances. Each measurement holds a possibility. Each observation strengthens the foundation for what will come next. The question that guides them remains simple. If life is out there, how can we detect its presence with clarity and confidence? Humanity stands at the threshold of that answer, supported by the machines that serve as our eyes, our ears, and our tools across the cosmic landscape. Earth feels complete. Oceans move in slow rhythms. Clouds trace shifting patterns. Continents rise and weather away across long cycles of wind, water, and heat. Life covers nearly every surface. Yet when we step back and view our planet from space, a larger truth appears. Earth is only one world orbiting an average star in a galaxy filled with hundreds of billions of stars. Somewhere among them may be planets as stable, blue, and life-bearing as our own. For most of human history, this idea remained imagination. Today it becomes measurable science. Telescopes can detect the dimming of a star when a planet crosses in front of it. Instruments can read the chemistry of an atmosphere by splitting starlight into narrow bands. Models can simulate the climate of a distant world and predict where oceans might form. The search for the next Earth has shifted from myth to observation. It now rests on data that arrives from thousands of light years away. Finding another Earth requires more than identifying a planet the same size as ours. A habitable world must maintain liquid water, protect its surface with an atmosphere, and regulate temperature through long-term cycles. It must lie at the right distance from its star. It must receive stable light without violent bursts of radiation, must have gravity strong enough to hold an atmosphere but not so strong that its surface becomes locked under crushing pressure. These conditions depend on both the planet and its star. They form a balance that must remain stable across billions of years. Even within these boundaries, the range of possible habitable worlds is enormous. Some may be warmer or colder than Earth, yet still support oceans. Some may be covered entirely in water. Some may have continents shaped by different forms of geology. Some may orbit red dwarf stars and experience permanent day on one side and permanent night on the other. Habitability is not a single template. It is a spectrum of environments defined by energy, chemistry, and time. The machines that search for these worlds now operate across many parts of the sky. They watch thousands of stars at once and record tiny variations in brightness. They collect spectra that reveal water vapor, carbon dioxide, and thermal patterns. They study faint signals that drift through interstellar dust. Each detection carries the possibility that a world similar to ours exists far beyond the solar system. As we refine these tools, the idea of another Earth becomes more than speculation. It becomes a target, a world hidden in the glow of its star, a place where oceans might form under distant skies, a surface shaped by weather geology and chemical cycles that mirror or diverge from our own. The hunt for these planets has only begun, yet the first hints already appear. Somewhere among the stars, the next Earth waits to be seen. To search for a world like Earth, scientists must first define what makes a planet habitable. The term sounds simple, yet the requirements stretch across physics, chemistry, and climate. Earth maintains a narrow range of temperatures that allow water to remain liquid. Its atmosphere protects the surface from radiation while trapping enough heat to prevent global freezing. Its geology recycles carbon minerals and heat. Its magnetic field shields the surface from high-energy particles from the sun. These systems operate together. If any major component fails, habitability collapses. The region around a star where temperatures permit liquid water is called the habitable zone. Yet this zone is not enough. A planet inside it may still be barren. If it lacks an atmosphere, water will evaporate into space. If the atmosphere is too thick, the surface may grow as hot as Venus. If volcanic activity stops, carbon cycles may freeze and the climate may lock into a snowball state. If the star produces intense flares, radiation may erode the atmosphere faster than it can be replenished. True habitability depends on long-term balance, not distance alone. Each planet must combine pressure, composition, and temperature in a delicate way. Surface pressure determines whether liquid water can remain stable. Too low and water boils away. Too high and oceans may become superheated and unstable. The chemistry of the atmosphere controls heat flow. Molecules like carbon dioxide and water vapor trap warmth. Nitrogen helps regulate temperature by providing bulk without strong greenhouse effects. Clouds can cool or warm depending on their altitude and thickness. These factors interact through complex feedbacks that define climate stability. The planet's interior also influences habitability. Active geology can produce volcanoes that release gases and recycle minerals. Plate movement can redistribute heat and reshape coastlines. Magnetic fields arise from molten cores and act as shields against stellar radiation. Without these protective layers, the upper atmosphere may be stripped away by charged particles. Mars demonstrates this vulnerability. Its magnetic field faded early in its history and its atmosphere thinned until surface conditions grew hostile to liquid water. Stars add another layer of complexity. The color and temperature of a star determine the wavelength of light received by a planet. Cooler stars emit more infrared radiation, which interacts differently with atmospheric molecules. Hotter stars produce more ultraviolet radiation that can break apart water and other compounds. The stability of a star also matters. A world orbiting a calm star may remain habitable for billions of years. A world orbiting a volatile star may experience repeated radiation events that disturb its climate. These combined factors show why Earth cannot be used as a strict template. Habitable planets may exist under different conditions. Some may orbit dim stars with narrow zones of warmth. Others may orbit bright stars with wide temperate belts. Some may have thick atmospheres that support global oceans. Others may have thin atmospheres with scattered lakes and icy regions. Habitability is a broad category shaped by many interacting systems. As telescopes improve, scientists now examine these factors in distant worlds. They measure atmospheric composition, estimate surface temperatures, and model heat flow. They compare these findings with climate simulations that predict which environments can support liquid water for long periods. Through this approach, the search for the next Earth shifts from guessing to testing. It becomes a scientific framework that guides observations toward the most promising worlds. Every potential Earth begins with its star. The star sets the temperature range, the radiation environment, and the length of a planet's seasons. It controls how quickly a world loses or gains heat. It influences the chemistry of the upper atmosphere. Without understanding the star, the planet cannot be evaluated. Habitability depends not only on surface conditions, but also on the long-term behavior of the energy source that drives climate. Red dwarfs are the most common stars in the galaxy. They are small, cool, and long-lived. Their habitable zones lie close to the star, often at distances where planets complete an orbit in a few weeks. These worlds are easier to detect because their transits cause deeper dimming events. Yet proximity brings challenges. Red dwarfs release frequent flares that produce bursts of ultraviolet and X-ray radiation. These events can erode atmospheres or disrupt chemical cycles. Planets locked in close orbits may rotate slowly and show the same face to the star. This creates extreme temperature contrasts between permanent day and permanent night. Despite these difficulties, red dwarf systems remain strong candidates for habitable planets. Climate models show that thick atmospheres or global oceans can redistribute heat. Some simulations identify a twilight zone where temperatures remain stable. In this zone, winds carry warmth from the day side to the night side. The result is a band of mild conditions that could support liquid water. Telescopes target these systems frequently because the planets are easier to observe than those around larger stars. Sun-like stars offer a more familiar environment. Their habitable zones are wider and lie farther from the star. Planets in these zones can rotate freely without tidal locking. The light from such stars resembles the spectrum that reaches Earth. Photosynthesis, as we understand it, may operate more efficiently under this type of light. These stars also tend to be more stable than red dwarfs. They produce fewer violent flares and maintain steady brightness over long periods. This stability supports climate regulation on orbiting planets. Stars hotter than the Sun create different challenges. They shine brightly and emit more ultraviolet radiation. Their habitable zones lie far away, which reduces the likelihood of detecting planets through transits. More importantly, these stars live for shorter periods. Some last only a few 100 million years. This timescale may be too short for complex chemistry to develop stable ecosystems. Even if planets exist in the right temperature range, the star may change too quickly for life to emerge and adapt. The age of a star also plays a role. Young stars are often unstable. Their radiation output fluctuates and their winds can strip atmospheres from nearby planets. As stars mature, their brightness increases gradually. This shift can push planets out of the habitable zone over time. Earth itself will face this fate in the distant future as the Sun grows warmer. In contrast, older stars in quiet phases may offer long windows of stability. Planets orbiting them could maintain liquid water for billions of years. The search for the next Earth must consider these stellar factors. Astronomers classify potential targets by star type, age, activity level, and radiation spectrum. They track flares and measure magnetic behavior. They use these data to build models of how a star influences its planets over time. By understanding these influences, scientists can identify which systems are most likely to host planets with stable climates. As observations expand, a pattern becomes clear. Many planets lie in regions where temperature might permit liquid water, but only a fraction orbit stars that can support long-term stability. This realization guides future missions. Instruments focus on stars with moderate radiation and long lifespans. They prioritize systems where planets can survive billions of years without losing their atmospheres. Through this method, the search moves closer to identifying true Earth analogues. When the first planets outside the solar system were identified, most were giants larger than Jupiter. Their immense size created deep signals that early detectors could find with ease, but scientists wanted smaller worlds. They wanted rocky planets with temperatures that allowed liquid water. They wanted the first evidence that Earth was not alone in its basic structure. The breakthrough came when space telescopes began watching thousands of stars continuously. By measuring tiny changes in brightness, these missions revealed planets that matched the scale of Earth. Kepler played a central role in this discovery. It monitored more than 100,000 stars and recorded every faint dip in their light. From this long watch, Kepler uncovered thousands of planets. Among them were several Earth-sized candidates in or near the habitable zone. Kepler 442, Kepler 438b and Kepler 3457b were among the earliest examples. Each had a radius close to Earth's. Each orbited a star with enough warmth to allow liquid water. These planets became the first promising hints, though many details about their atmospheres and surfaces remained unknown. The TRAPPIST-1 system delivered another major milestone. This star is a small red dwarf with 7 rocky planets packed in tight orbits. 3 of the planets lie within the region where temperatures could permit liquid water. Their densities indicate solid rocky interiors. Their transits are deep and frequent, making them ideal for atmospheric studies. This system showed that entire families of Earth-sized worlds could form around small stars. It also highlighted the importance of stellar activity, because flares from the star could influence atmospheric stability. Proxima Centauri b created global attention due to its proximity. It orbits the closest star to the Sun at a distance where temperatures might allow liquid water. Its mass suggests a rocky composition. It receives a level of energy similar to Earth, though its star produces intense bursts of radiation. Despite these challenges, Proxima b remains one of the most studied exoplanets, because future instruments may one day image it directly. Its orbit around a nearby star makes it one of the strongest candidates for detailed atmospheric analysis. Another group of discoveries involves planets around quiet red dwarfs with stable light curves. These stars offer a calmer environment than many active dwarfs. Planets such as LHS 1140b fall into this category. They orbit stars with moderate radiation levels and sit within or near the habitable zone. Their sizes and masses match the rocky category. Their orbits allow repeated observations without strong interference from stellar flares. They serve as test cases for studying how atmospheres survive in cool star systems. These early discoveries share key limitations. Size and mass measurements provide clues, but they cannot confirm surface conditions alone. A planet as small as Earth may still be covered by thick clouds that create extreme greenhouse heating. A world with the right mass may lack an atmosphere entirely. Density measurements suggest composition but do not reveal climate. Despite these gaps, the discoveries marked a turning point. They demonstrated that small rocky planets are common. They showed that the galaxy contains many potential homes for stable climates. With each new detection, the catalogue of Earth-like candidates expanded. Scientists refined their models. They identified which systems deserved deeper study with advanced telescopes. They analysed the relative brightness of stars and the visibility of atmospheric signals. These steps prepared the ground for a new generation of instruments. The next wave of observations would move beyond identifying planets. It would examine their atmospheres and search for the chemical markers that define habitability. The search had entered a new phase. The first Earth-sized planets had been found. The next challenge was to determine which of them could truly support stable oceans, protective atmospheres, and long-term energy cycles. The hunt for the next Earth shifted from discovery to characterization. When scientists imagine another Earth, the mind naturally gravitates toward blue oceans, white clouds, and scattered continents. But the universe creates rocky planets in many forms. Some resemble Earth in broad structure. Others differ in density, surface chemistry, or internal layering. These differences shape climate geology and long-term stability. Understanding them is essential to identifying which worlds can become true Earth analogues. Rocky planets come in several categories based on composition. Some are iron-rich with heavy cores that create strong gravity and high surface pressure. These planets may hold dense atmospheres that trap heat. Others contain large fractions of silicates and lighter minerals. They may support thinner atmospheres and cooler climates. Density measurements help classify these interiors, but they reveal only part of the story. Surface conditions depend on how heat moves through the crust, how often the planet erupts, and how quickly it exchanges gases with the sky. Super-Earths add further complexity. They are larger than Earth, but smaller than Neptune. Their masses suggest that many are rocky. Their stronger gravity can maintain deep oceans and thick atmospheres. Some models show that super-Earths may regulate climate more effectively than Earth, due to stronger convection in their mantles. These processes could drive long-lasting volcanic cycles that recycle carbon and support stable temperatures. At the same time, extreme pressure at depth may restrict plate movement or limit the formation of continents. The balance between water pressure and rock defines whether these planets become ocean-covered worlds or mixed terrain environments. Ocean worlds represent another class. They may contain global seas tens or even hundreds of kilometers deep. Beneath these oceans may lie layers of high-pressure ice or silicate mantles with active chemistry. The absence of continents changes how nutrients cycle and how climate stabilizes. Without exposed land, chemical weathering and carbon exchange follow different pathways, yet life could still emerge in such environments. Hydrothermal activity on the ocean floor could provide energy sources similar to those on Earth's seafloor. Some planets exist at the boundary between rocky worlds and mini-Neptunes. These bodies may have started with thick hydrogen atmospheres that later escaped into space. As these atmospheres eroded, bare rocky cores remained. This process depends on the intensity of the star's radiation. It creates a pathway where worlds that were once non-habitable can transition into temperate rocky planets. These planets may hold thin atmospheres that can be analysed with powerful telescopes. Their evolution reveals how dynamic planetary systems can be. Desert worlds also appear frequently in models and observations. These planets may have limited surface water but retain stable climates through strong atmospheric circulation. Large temperature gradients between day and night create winds that transport heat. Thin layers of ice may persist in polar regions or deep basins. Even with small amounts of water, local habitats could develop around volcanic features or areas where pressure allows liquid water to appear temporarily. The variety of terrestrial architecture shows that Earth is a single example within a broad spectrum. True Earth analogues may match Earth closely. Earth cousins may differ in size but share climate stability. Earth siblings may share chemistry but orbit different kinds of stars. Some may be warmer and covered in deep oceans. Others may be cooler with scattered lakes. Habitability emerges from combinations of factors rather than strict duplication. As astronomers detect more small planets, they refine their categories and simulations. They examine how mass radius and atmospheric signals correlate with surface environments. They study how stellar radiation shapes atmospheric loss or retention. They compare these findings with geological models. Through this work, the search expands beyond cloning Earth. It becomes a search for environments capable of long-term liquid water and chemistry, regardless of whether the surface looks familiar. This broader view changes the hunt. Instead of seeking a single blueprint, scientists analyze entire classes of worlds. Each class offers pathways to stability. Each presents distinct challenges for observation. Together they reveal that many planets may reach conditions suitable for life, even if their structure differs from that of Earth. A planet's atmosphere holds the clearest clues to its potential for life. It regulates temperature, controls the movement of heat, and protects the surface from harmful radiation. It carries signatures of water, minerals, and chemical reactions. It reveals whether a planet can support stable climates, or whether it drifts toward extremes. For distant worlds, the atmosphere is often the only layer we can study. Through it, scientists infer the conditions below the clouds and across the surface. The first question is whether an atmosphere exists at all. Some planets lose their air to space because stellar radiation strips molecules from the upper layers. Others keep thick blankets of gas that trap heat at dangerous levels. A world without air cannot hold liquid water for long. A world with too much air may become hostile to life due to pressure and heat. Measuring atmospheric depth is therefore essential. It shows whether the surface lies within the range where liquid water can remain stable. Chemistry is the next step. Molecules absorb and emit light at precise wavelengths. Water vapor, carbon dioxide, methane, and ozone each leave distinct patterns in a spectrum. These patterns reveal how heat moves through the atmosphere and how energy enters and leaves the system. They show whether clouds reflect sunlight or trap warmth. They clarify whether greenhouse effects remain balanced, or whether a planet approaches runaway heating or global freezing. Oxygen often receives attention because it supports life on Earth. Yet oxygen alone cannot prove habitability. It can arise through non-biological processes such as the breakdown of water under strong ultraviolet radiation. What matters is imbalance. A combination of gases that should not coexist for long periods may indicate ongoing replenishment. On Earth, the presence of oxygen along with methane reflects biological activity. In distant systems, scientists search for similar disequilibrium patterns. They analyze ratios, absorption depths, and temperature layers to understand how these gases interact. Clouds and haze complicate the picture. These layers can mask spectral signatures or change the planet's reflectivity. High-altitude clouds may cool a surface by reflecting sunlight. Thick haze may trap heat or hide chemical signals. Some worlds may have permanent cloud belts shaped by rotation and atmospheric circulation. Others may experience seasonal changes that alter the appearance of the spectrum. Observing multiple transits helps reveal these shifts and distinguishes stable patterns from temporary deviations. Surface temperature cannot be measured directly for most planets, but it can be estimated. Infrared signals show how much heat escapes into space. Comparing this with the amount of starlight a planet receives gives clues about climate. A world with strong greenhouse effects may radiate less heat than expected. A world with thin air may radiate too much. These measurements allow scientists to build models that predict how oceans, ice, and land might form. Some planets show signs of volcanic gases. These emissions may indicate an active interior capable of recycling minerals and releasing heat. Geological activity supports long-term habitability by maintaining carbon cycles and preventing climate stagnation. Detecting sulfur compounds or carbon monoxide at specific altitudes can hint at volcanic processes. Although these signals are faint, they provide valuable insight into the energy sources available on a planet. Through these observations, scientists piece together the environmental story of each world. They determine whether conditions can support liquid water. They evaluate whether the atmosphere can survive for billions of years. They compare the chemistry with models that describe how life may gain a foothold. The atmosphere becomes a natural archive of a planet's history and potential. For planets beyond our reach, it serves as the primary gateway to understanding whether they could ever resemble Earth. As more data arrives from advanced telescopes, atmospheres that once appeared featureless now reveal detailed structure. Patterns emerge across many planets, and these patterns show which conditions favor stability. Each spectrum becomes a window into a distant climate. Each measurement brings the search for the next Earth closer to reality. The James Webb Space Telescope pushed the search for Earth-like planets into a new era. Earlier missions could find planets by tracking shadows or measuring the wobble of stars. Webb can go further. It can examine the faint light that passes through a planet's atmosphere and identify the molecules suspended within it. This ability transforms distant worlds from silhouettes into environments with measurable chemistry. For the first time, scientists can study the atmospheric structure of small rocky planets that orbit other stars. Webb operates in infrared wavelengths where many key molecules reveal their signatures. Water vapor absorbs strongly in this range. Carbon dioxide and methane leave deep fingerprints. Even thin atmospheres produce patterns that Webb can detect. When a planet crosses in front of its star, a small fraction of starlight filters through the upper layers of the atmosphere. Webb's spectrographs separate this light into narrow bands. By comparing spectra before and during transit, the telescope identifies which wavelengths are missing and which molecules cause the absorption. Rocky planets create faint signals, yet Webb has already measured several of them. Observations of worlds in the TRAPPIST-1 system show whether their atmospheres remain intact or have been stripped away by stellar radiation. Some spectra reveal flat lines, which suggests a lack of thick air. Others suggest layers of haze or clouds that mask deeper chemistry. These findings help scientists determine whether conditions remain stable enough to allow long-term liquid water. Even a null result is valuable. It tells researchers which planets no longer hold the ingredients for habitability. Webb also studies temperature gradients across planetary surfaces. By observing infrared light when a planet moves behind its star, the telescope measures how much heat the planet emits. This technique reveals whether heat circulates evenly through the atmosphere or remains trapped on one side. For tidally locked worlds, this data distinguishes between extreme day-night contrasts and moderate climates supported by strong winds. These measurements show how atmosphere and rotation interact to shape surface conditions. One of the most important contributions from Webb involves the study of planets around cool stars. These stars are abundant and many host Earth-sized planets. Their dim light allows easier detection of atmospheric absorption features. Webb can identify carbon dioxide in these atmospheres and measure the thickness of hazy layers. It can detect thermal signals that indicate whether clouds reflect enough starlight to keep temperatures within a habitable range. These combined observations guide researchers toward the most promising candidates for deeper study. Webb's sensitivity also opens the door to evaluating new classes of planets. Ocean worlds with thick atmospheres, often called Hycean candidates, produce strong infrared signals. Webb can measure the presence of water-rich vapor, or look for compounds created through interactions between oceans and light. It can observe changes across multiple transits to determine whether climate patterns remain stable. These studies refine models of worlds that differ from Earth yet may still support life. Although Webb cannot confirm life, it narrows the field. It identifies planets with atmospheres that resemble those capable of supporting liquid water. It distinguishes between barren rocks and worlds with complex climate systems. It measures the radiation environment created by the host star and determines whether the atmosphere can survive long-term. Every spectrum helps build a clearer picture of which planets deserve future missions. Webb stands at the midpoint of the search. It extends far beyond the capabilities of Kepler and TESS, yet it also prepares the foundation for telescopes that will follow. The data it collects will shape the design of instruments that aim to detect continents, clouds, and seasonal changes on distant planets. By revealing the chemistry of small worlds, Webb brings the search for the next Earth into sharper focus. As telescopes expanded their reach, scientists began to notice a new type of planet that did not resemble Earth, yet still showed potential for habitability. These worlds have deep global oceans and thick hydrogen-rich atmospheres. They are called Hycean planets. Their temperatures may fall within the range where liquid water remains stable. Their atmospheres create strong greenhouse effects that keep oceans warm even around faint stars. Their larger sizes make them easier to study than true Earth-sized planets. These features raised a striking question. Could life be more common on Hycean worlds than on Earth clones? Hycean planets differ from Earth in key ways. Their oceans may stretch for thousands of kilometers without interruption. Their atmospheres may extend far above the surface. Pressure and temperature rise quickly with depth. Light may penetrate only short distances into the ocean. These conditions create environments that resemble deep ocean layers on Earth rather than shallow coastal zones. Life, if present, would need to adapt to low light and high pressure. Yet similar ecosystems thrive near hydrothermal vents on Earth's seafloor. Chemistry in these environments relies on thermal and mineral energy rather than sunlight. One advantage of Hycean planets lies in their detectability. Thick atmospheres produce strong absorption features in infrared light. Webb can measure these signals more easily than those from thin atmospheres like Earth's. Molecules such as water vapor and methane appear clearly in spectra. If unusual combinations of gases exist, they may stand out. In contrast, Earth-sized planets with thin atmospheres produce weaker signals that require long observation times. Hycean candidates provide early opportunities to test atmospheric retrieval techniques and learn how climate behaves on water-dominated worlds. Critics highlight potential drawbacks. High pressure at depth may prevent geological cycles that recycle minerals and stabilize climate. Without exposed land, chemical diversity may be limited. Deep oceans may trap nutrients far below regions where light or heat are sufficient for metabolism. Hydrogen-rich atmospheres may produce hazes that block starlight. These factors could restrict biological activity or limit the complexity of life. Researchers caution that habitability depends not only on water, but also on chemical gradients, energy flow, and long-term stability. Another challenge is the formation of these planets. Some models show that Hycean worlds may evolve from mini-Neptunes. These bodies begin with thick hydrogen atmospheres and lose mass over time. If the atmosphere thins enough, the planet may enter the temperature range where oceans form. This pathway creates vast ocean surfaces, yet the origin of such environments remains uncertain. Their internal chemistry may differ sharply from Earth's. The balance between atmospheric thickness, ocean depth, and heat absorption determines whether surface conditions remain stable. Observations from Webb have already influenced the debate. Some early candidates once labelled as Hycean may not fit the model. Their atmospheres may be thinner or contain unexpected molecules. Others may lack the strong absorption features predicted by theoretical models. These findings show that Hycean classification requires careful analysis. A planet must show both atmospheric depth and temperature conditions consistent with warm global oceans. Without both, it may fall into a different category. Despite uncertainties, Hycean planets broaden the search. They show that habitability may not require continents or thin air. It may arise in environments where heat and chemistry interact in ways unfamiliar on Earth. These worlds highlight the importance of flexibility in defining habitability. They encourage researchers to consider multiple pathways to stable liquid water. They demonstrate that the next Earth may not look like Earth. It may be a world where oceans cover every surface. Clouds hang high above the horizon, and light filters softly through thick layers of atmosphere. As the debate continues, Hycean worlds remain central targets for atmospheric studies. They challenge assumptions. They expand the range of environments where life may emerge. They shape the strategies used to identify habitable planets. Through them, scientists refine their understanding of what it means for a world to support life across the galaxy. Understanding a distant world requires more than measuring its size and atmosphere. Climate determines whether oceans freeze, boil, or remain stable across long timescales. It controls wind patterns that distribute heat. It shapes cloud formation and the balance between evaporation and rainfall. Since these processes cannot be observed directly on most exoplanets, scientists rely on climate simulations. These models extend the principles used to study Earth and adapt them to worlds with different rotation rates, star types, and atmospheric compositions. Global climate models, known as GCMs, begin with basic physics. They calculate how sunlight enters the atmosphere and how heat escapes into space. They track the movement of air as it rises, cools, and sinks. They simulate how oceans absorb energy and release it slowly through currents. They include chemical reactions that influence greenhouse effects. When applied to Earth-sized planets around other stars, these models reveal climate states that differ from anything found in the solar system. Tidally locked planets present unique challenges. One side faces the star continuously. The other remains in darkness. Without atmospheric circulation, the day side could reach extreme temperatures, while the night side freezes solid. Yet models show that a planet with a dense atmosphere can move heat efficiently. Winds may flow from the illuminated hemisphere toward the dark hemisphere. Clouds may form on the day side, reflecting starlight and preventing runaway heating. These processes create a stable band of mild temperatures around the terminator, the dividing line between day and night. In this region, surface water could remain liquid. Slow-rotating planets produce different patterns. They develop thick cloud layers above the substellar point where sunlight strikes most directly. These clouds reflect significant amounts of energy and cool the surface below. The effect expands the habitable zone, allowing planets closer to their stars to maintain stable climates. Fast-rotating planets, in contrast, develop jet streams that shift heat toward the poles. These variations show how rotation controls climate far beyond Earth's familiar patterns. Ocean depth also plays a major role. Deep oceans can store heat and release it, slowly moderating temperature swings. Shallow oceans respond more quickly to stellar variations. Models that include ocean currents reveal how heat moves across a planet. On some worlds, warm water may travel from the day side to the night side, reducing temperature extremes. On others, strong winds may drive upwelling that brings cold, nutrient-rich water to the surface. These processes influence cloud formation and atmospheric chemistry. Volcanic activity and geological cycles appear in advanced models as well. Active interiors release gases that influence climate stability. Large eruptions can inject heat-absorbing particles into the atmosphere, or produce reflective aerosols that cool the surface. Over millions of years, these cycles shape the distribution of carbon, sulfur, and water. A planet with continuous geological activity may maintain a stable atmosphere. A geologically quiet world may drift toward extremes. Cloud behavior remains one of the most difficult factors to simulate. Clouds can cool or warm depending on altitude and thickness. Their movement depends on local temperature gradients and atmospheric pressure. On some planets, permanent cloud belts may circle the equator. On others, clouds may cluster around the poles or shift with seasons. High-altitude haze can mask atmospheric signatures and complicate observations. Models must account for these effects to interpret spectra correctly. Climate simulations help scientists evaluate which planets deserve closer study. By combining models with observations, researchers can estimate surface conditions even when direct measurements are impossible. They can identify worlds that remain stable across long periods and filter out those prone to climate collapse. They can predict whether oceans might form, whether ice might dominate, or whether a planet could remain temperate. These simulations guide future telescope observations. When a model predicts a strong climate signal, astronomers focus their instruments on wavelengths that reveal that signal. When a model predicts unstable conditions, scientists may prioritize other targets. Through this partnership between theory and observation, researchers transform distant planets from unknown points of light into worlds with weather seasons and long-term environmental histories. Climate modeling does more than describe these planets. It prepares scientists for the day when the first true Earth analog emerges from the data. It provides a framework for interpreting its atmosphere, its clouds, and its thermal behavior. It helps answer the question that drives the entire search. Under what conditions can a distant world sustain a stable environment where life could arise and endure? The search for Earth-like planets depends on machines that can isolate faint signals hidden in starlight. Kepler revealed how common small planets are. Webb exposed their atmospheres. But the next generation of observatories will take the search further. They will measure climates directly and capture reflected light from distant worlds. They will reveal continents, clouds, and seasonal changes. They will move the field from detection to true characterization. This shift requires telescopes with powerful mirrors, stable optics, and instruments that can filter out the glare of stars. One of the most ambitious projects is the Habitable Worlds Observatory. It is designed to observe Earth-sized planets in the habitable zones of Sun-like stars. To achieve this, it must suppress starlight with extraordinary precision. The telescope will likely use advanced coronagraphs that block the central disk of a star and reveal the faint glow of orbiting planets. Some designs also include starshade spacecraft. These spacecraft fly tens of thousands of kilometers from the telescope and cast a precise shadow that dims starlight without touching the planet's own light. This approach allows direct imaging of Earth-level brightness contrasts. Direct imaging changes everything. Instead of interpreting spectra from transit events, astronomers can capture photons reflected from the planet's surface or atmosphere. Reflection carries information about clouds, oceans, and land. Polarized light reveals whether the surface is smooth or rough. Color variations show differences between vegetation, mineral types, or cloud cover. Time variation shows rotation periods and seasonal shifts. These measurements allow scientists to create maps of distant worlds, though at very coarse resolution. Another major instrument on the horizon is the extremely large telescope. Its mirror spans more than 30 meters. It gathers immense amounts of light and resolves fine details across distant systems. With adaptive optics that correct for atmospheric turbulence, the telescope can study planets around nearby stars at wavelengths that complement Webb. It can measure temperature gradients, detect volcanic gases, and observe how clouds move across the night side of a planet. Combined with infrared data, these measurements help confirm climate models. Radio observatories also play a role. The Square Kilometre Array will map magnetic interactions between stars and planets. Magnetic fields are crucial because they protect atmospheres from high-energy particles. Detecting these interactions reveals whether a planet may have retained its atmosphere across billions of years. This adds another layer to habitability assessment. A planet may orbit in the right zone, but without a magnetic field, its atmosphere may be vulnerable to erosion. Future ultraviolet telescopes will examine chemical processes that shape upper atmospheres. Ultraviolet light breaks molecules apart and influences how gases escape into space. Measuring these effects helps scientists determine whether a planet can keep its air over long timescales. By studying ultraviolet wavelengths, researchers learn how atmospheres evolve and whether they remain stable enough for oceans to persist. Other missions focus on transit detection with higher precision. New satellites will monitor large sections of the sky for small dips in brightness caused by Earth-sized planets. They will gather thousands of transits for individual systems. This long baseline of data reveals orbital changes, planet-planet interactions, and atmospheric variations caused by seasons. The combination of transit data, direct imaging, and spectroscopy creates a multi-dimensional view of each candidate. As these machines come online, the search becomes more focused. Instead of scanning the entire sky, scientists target nearby stars where detailed follow-up is possible. They prioritize quiet stars with stable brightness. They identify systems where planets transit at angles that allow repeated atmospheric measurements. This strategic approach increases the likelihood of finding planets with conditions similar to Earth. The next generation of observatories will not merely detect worlds. They will study them as environments with complex dynamics. They will examine their weather chemistry and long-term evolution. Through these machines, the search for Earth 2 becomes a structured scientific mission. It becomes a precise effort to identify which worlds possess the stability, chemistry, and energy balance required for life. As telescopes reveal atmospheres and climates, another layer of the search emerges. It involves identifying patterns that nature struggles to produce without ongoing processes. These patterns are called biosignatures. They arise when chemical reactions in an atmosphere remain out of balance. They appear when energy flows in ways that match biological cycles. They take shape when gases coexist that should destroy each other unless they are being replenished. On Earth, oxygen and methane form such a pair. Their simultaneous presence signals continuous activity. In distant systems, similar indicators may point toward life. A biosignature can be a single molecule or a combination of several. Oxygen is one possibility. Methane is another. Nitrous oxide, sulfur compounds, and organic haze also appear in models of biological activity. None of these gases alone can confirm life. Each has geological or photochemical pathways that can mimic biology. What matters is context. Scientists compare the amount of light the planet receives, the structure of the atmosphere, and the temperature of the surface. They model how known processes produce these gases. If none of these pathways fits, the observation's biological activity becomes a statistical explanation. Some worlds may show biosignatures driven by oceans. Others may show them through volcanic cycles that influence atmospheric chemistry. Still others may show them through interactions between light and organic molecules suspended in upper layers. The search requires careful analysis of absorption features, temperature profiles, and cloud behavior. Webb has provided the first hints, though no confirmed biosignature has yet emerged. Future telescopes will refine this work by examining planets across wider spectral ranges. Technosignatures extend the search into another category. These indicators arise not from biology but from advanced civilizations. They include narrow radio signals, artificial light leakage, industrial gases, or waste heat. Radio telescopes monitor nearby stars for patterns that stand out from natural noise. Sensitive instruments search for pulses or continuous carriers at stable frequencies. Optical telescopes examine starlight for periodic dimming that could hint at structures built in orbit. Infrared telescopes measure heat distribution for signs of large-scale energy use. No confirmed technosignature has been detected, yet the search provides valuable insights. It demonstrates how sensitive our instruments have become. It explores how energy use might appear when viewed across interstellar distances. It reveals which signals are easy to identify and which require more careful analysis. This work shapes the design of future detectors and helps scientists understand which environments deserve deeper attention. False positives remain an important challenge. Stellar activity can mimic chemical imbalance. Clouds can hide or distort atmospheric signatures. Geological cycles can produce gases that resemble biological byproducts. Cosmic dust can affect infrared measurements. To address these issues, researchers combine multiple lines of evidence. They examine temperature depth profiles. They look for consistent signals across many observations. They compare spectra taken at different points in the planet's orbit. Only when multiple indicators align does a candidate move into the high-interest category. Biosignature studies depend strongly on the host star. Light from red dwarfs interacts differently with atmospheric molecules than light from sun-like stars. Strong ultraviolet bursts can break apart water and create oxygen even in the absence of biology. Carbon dioxide may appear more or less prominent depending on the star's spectrum. Scientists must consider these factors to avoid misinterpretation. The search becomes a careful balance between data and model observation and theory. Even with these difficulties, progress continues. Each atmosphere measured by Webb supplies constraints on climate and chemistry. Each transit reveals new structural details. When next-generation telescopes begin operations, they will collect data with far higher precision. They will identify subtle patterns in light that earlier missions could not detect. Through this process, the boundary between unknown and possible becomes clearer. Biosignatures and technosignatures define the frontier of the search. They represent the point where atmospheres, climates, and chemistry become more than physical data. They become indicators of processes that may support or arise from life. They show that the hunt for Earth 2 is not only about temperature and pressure, it is about recognizing patterns that require continuous energy flow, patterns that hint at complexity, patterns that bring the search closer to the first signs of life beyond the solar system. With thousands of planets identified and hundreds studied in detail, scientists now focus on a small group of exceptional candidates. These worlds lie at distances from their stars where liquid water may survive. They have densities that match rocky composition. Some show hints of stable atmospheres. Others lie around stars calm enough to support long-term climate balance. None are confirmed Earth analogues, yet each holds a piece of the larger puzzle. Together they represent the best opportunities to find a world that resembles our own. One of the leading candidates is Kepler 442b. It is slightly larger than Earth, and orbits a star cooler than the Sun. Its position places it within a temperature range where water could remain liquid. The star is relatively quiet, which reduces atmospheric loss. Observations suggest that the planet is dense enough to be rocky. Although Webb has not yet measured its atmosphere, models show that a moderate climate is possible if the planet retained a stable layer of gases. Its distance makes detailed study difficult, but it remains one of the strongest early finds. Another promising world is LHS 1140b. It orbits a cool dwarf star within a zone where temperatures may permit oceans. The star shows less flare activity than many dwarfs, increasing the chance that the planet's atmosphere survived. Early measurements indicate a high mass for its size, suggesting an iron-rich interior. This structure could support a strong magnetic field. If the atmosphere is intact, the climate may remain stable despite the star's low brightness. Webb has targeted this system to determine whether the planet holds a detectable layer of gases. Proxima Centauri b stands out because of its proximity. It orbits the star closest to the solar system and receives an amount of energy similar to Earth. Its rocky mass and temperate orbit place it among the most studied candidates. Yet its star emits frequent bursts of radiation that may erode the atmosphere. Webb and ground-based telescopes monitor the system to understand how often these flares occur and how intense they are. If Proxima b maintains a protective magnetic field, it may preserve its atmosphere despite the harsh conditions. Its closeness makes it an ideal target for future direct imaging missions. The TRAPPIST-1 planets remain central to the search. 3 lie within or near the habitable zone. Their sizes are close to Earth's. Their orbits allow repeated transits that enable detailed atmospheric analysis. Webb has observed several of these worlds and detected signs that at least some may have thin or eroded atmospheres. Others show hints of haze or clouds. Although the system faces challenges from stellar activity, its compact layout provides opportunities unmatched by most planetary systems. Each measurement taken from TRAPPIST-1 helps refine models of rocky planets around dwarf stars. K218b represents a different category. It is larger than Earth and may contain a deep ocean beneath a thick atmosphere. Webb detected carbon-bearing molecules in its spectrum. Although this discovery remains under debate, it demonstrates how sensitive instruments can identify subtle patterns. K218b may not resemble Earth, yet it may host conditions suitable for complex chemistry. Its atmosphere remains a valuable test case for methods that will later be applied to Earth-sized planets. Scientists also target planets around bright, quiet stars. These stars provide strong, stable signals that improve the precision of atmospheric measurements. Worlds such as HD 103197b and TOI 700 fall into this category. Although their atmospheres have not yet been confirmed, their host stars offer favourable conditions for long-term habitability. These systems will become high-priority targets for future direct imaging telescopes. As the list of candidates grows, researchers analyse which planets deserve repeated observation. They evaluate orbital stability, stellar radiation patterns, and atmospheric retention. They compare the strength of molecular fingerprints and the consistency of thermal signals. They use climate models to identify which worlds may support liquid water across millions or billions of years. Through this process, the field narrows from thousands of discoveries to a few dozen strong possibilities. These planets are not confirmed Earth twins, but they form the core of the search. They represent environments where the balance of temperature, radiation, and chemistry aligns with what we understand about habitability. They show how diverse Earth-like worlds can be. Some orbit bright stars, others orbit cool dwarfs. Some may host deep oceans. Others may hold continents under familiar skies. Each one brings scientists closer to answering the central question: how common are worlds like ours in the galaxy? Even with advanced telescopes and detailed climate models, direct searches can reveal only a fraction of all habitable planets. Most worlds remain hidden. Some orbit stars too faint for current instruments. Others sit at angles that never create measurable transits. Many lie beyond the reach of spectroscopy. To estimate how many Earth-like planets truly exist, scientists turn to statistics. They analyze detection rates correct for observational bias and infer how common habitable conditions may be across the galaxy. One of the most important quantities is eta Earth. This value represents the fraction of Sun-like stars that host at least one Earth-sized planet in the habitable zone. Kepler provided the first meaningful constraints. By measuring thousands of transits, the mission revealed how often small planets appear around different types of stars. For Sun-like stars, the data suggest that roughly 1 in 5 may host a planet with a size and temperature range similar to Earth. The exact number remains uncertain, yet even the lowest estimates point toward vast populations of potentially habitable worlds. Detection bias plays a major role. Transit surveys can identify only planets whose orbits align with Earth's line of sight. This geometry excludes most systems. To correct for this, scientists model the distribution of orbital tilts. They calculate how many planets must exist for a certain number to be visible. These models reveal that the true population of small planets far exceeds the number detected. For every world observed, dozens more likely orbit unseen. Stellar demographics also influence estimates. Red dwarfs dominate the galaxy. They are smaller and cooler than the Sun, but they host numerous small planets. Kepler and TESS data show that rocky planets around red dwarfs appear more frequently than around larger stars. Although flare activity poses challenges to habitability, some red dwarfs remain calm for long periods. Their long lifespans allow stable climates to persist across billions of years. When included in population models, these stars significantly increase the predicted number of temperate planets. Planet formation theory further supports high occurrence rates. Simulations of protoplanetary disks show that rocky planets form naturally as dust grains grow into pebbles, then into planetesimals, and finally into full-sized bodies. This process appears robust across a wide range of disk masses and star types. Water-rich material also forms easily in outer regions of disks, and can migrate inward to deliver oceans to forming planets. These findings suggest that the ingredients for habitability are common outcomes of planetary evolution. The metallicity of stars provides another clue. Stars with higher heavy element content tend to host more planets, including rocky ones. Observations of stellar populations in different parts of the Milky Way show that many regions contain stars with metallicities equal to or greater than the Sun's. This supports the idea that Earth-like planets should appear throughout the galactic disk, not only in a narrow band near the solar neighborhood. Gravitational microlensing surveys add a complementary perspective. These surveys rely on the bending of light from background stars when a foreground system passes in front of them. This technique can detect planets that do not rely on transits. It is especially sensitive to planets at moderate distances from their stars. Early results imply that Earth-mass planets may be extremely common, even around stars that would never produce observable transits. When all methods are combined, statistical models converge on a striking conclusion. The Milky Way likely hosts billions of rocky planets with temperatures where liquid water could exist. Even if only a fraction maintain stable atmospheres, the number of potential Earth analogues remains enormous. The galaxy is not sparsely populated with habitable environments. It may be filled with them. Despite this abundance, finding the nearest true Earth analogue remains challenging. The most promising candidates lie dozens of light-years away. Many are too faint for detailed observation. Future telescopes will shrink this gap, but for now, statistics provide the clearest view. They reveal that Earth's properties are not rare. They are part of a broader pattern written into the structure of the galaxy. These numbers set expectations for the final stage of the search. They shape strategies for future observatories. They suggest where scientists should look and how deeply they should probe. Above all, they show that the discovery of a true Earth analogue is not a question of possibility. It is only a question of time. If a true Earth analogue emerges from the data, the discovery will not end the search. It will launch a new scientific era. The first response would be to confirm the planet's atmosphere. Observatories across Earth and in orbit would scan its spectrum repeatedly. They would search for water vapor, carbon dioxide, and pressure signatures. They would measure temperature layers and the distribution of clouds. They would study the stability of the host star and track any flares that might disturb the atmosphere. These steps would build a complete environmental profile. Next comes the question of surface structure. Direct imaging telescopes would attempt to capture reflected light from the planet. Even a faint signal could reveal patterns that rotate over time. These patterns might indicate continents, oceans, or cloud belts. Variations in brightness would show the length of the planet's day. Seasonal changes might appear as shifts in color or reflectivity. Each observation would refine the map of this distant world. Although resolution would remain low, these measurements would transform the planet from a point of light into a physical environment. Once basic parameters are known, scientists would examine the planet's long-term stability. They would model orbital evolution to determine whether the climate remains steady across millions of years. They would evaluate whether interactions with neighboring planets influence tides or rotation. They would study the thickness of the atmosphere and whether it can resist erosion from stellar winds. If the world possesses a magnetic field, instruments may detect signatures of charged particle interactions. These factors reveal whether the environment can support persistent oceans and chemical cycles. If the atmosphere contains unusual combinations of gases, the next phase intensifies. Researchers would test whether geological processes alone can create the observed balance. They would model volcanic output, photochemical reactions, and atmospheric escape. They would analyze whether the detected molecules require continuous replenishment. If geological explanations fail, the planet enters a new category. It becomes a world with potential biosignatures. The search would then focus on ruling out every known false positive. As data accumulates, the public impact grows. Earth, too, would not be a distant curiosity. It would become a reference point. It would reshape discussions about how planets form, how climates stabilize, and how common habitable environments may be. Educational materials would change. Research funding would shift towards studying this world in detail. Simulation teams would build high-resolution climate models. Chemistry teams would model pathways for metabolic reactions. Universities would form new programs dedicated to comparative habitability. International space agencies would prepare long-term missions. Concepts for advanced telescopes would gain priority. Some designs include kilometer-scale mirrors in orbit. Others involve swarms of autonomous telescopes that combine their light to achieve extreme resolution. More ambitious ideas include laser-driven probes capable of reaching nearby stars within decades. These probes would carry cameras, spectrometers, and sensors designed to fly past Earth like worlds. Technologies for such missions remain theoretical today, but a discovered Earth analog would accelerate their development. The discovery would also influence how scientists interpret the solar system. Earth's uniqueness would be reframed. Instead of a rare anomaly, it becomes one of many. This shift alters expectations for the evolution of planets and the distribution of life. If one Earth exists nearby, more likely wait beyond the reach of current instruments. The galaxy would appear richer, not emptier. Habitable environments would become a standard outcome of planetary formation, not an exception. With each observation, Earth too would reveal more details. Its atmosphere may show layered clouds. Its rotation may produce mild seasons. Its oceans may glint through scattered light curves. Its climate may resemble Earth's or diverge in unexpected ways. These discoveries would refine our understanding of where life can emerge. They would show how temperature, chemistry, and energy flow combine to create stability. The moment Earth too enters the scientific record, the search expands in scope and purpose. It becomes a comparative study of two habitable worlds. It becomes a test of how universal Earth's conditions truly are. It becomes the foundation for a new branch of planetary science that examines life supporting environments across the galaxy. The discovery would not close the story. It would open the chapter that the final block will bring into focus. The search for another Earth begins with distant starlight and complex instruments, yet its meaning reaches far beyond measurement. Each spectrum, each dimming curve, and each climate model reshapes our understanding of where habitable environments can form. These observations reveal that stability is not rare. Oceans are not rare. Rocky worlds are not rare. Conditions that support complex chemistry may occur in many corners of the galaxy. The more we learn, the more the Milky Way appears populated with worlds that could sustain long periods of calm, warm environments. Earth itself becomes easier to understand through this comparison. Its oceans, atmosphere, and geology no longer stand alone. They fit within a larger pattern of planetary evolution. The processes that shaped its climate can arise on other worlds. The heat flow that drives its magnetic field has analogues elsewhere. The chemistry that cycles through its clouds and rivers follows principles that appear universal. This perspective does not diminish Earth. It connects it to a wider family of planets that follow similar physical rules. The instruments built for the search have changed our relationship with distance. Stars that once seemed unreachable now reveal the weight, size, and climate of the planets that orbit them. Telescopes sense heat on worlds dozens of light years away. Spectrographs detect molecules suspended in air that has never touched Earth. Models simulate the motion of winds on planets we will never visit in person. These achievements show how far observation has pushed into the domain once reserved for imagination. Finding Earth 2 would not solve every question. It would not answer how life begins or how it adapts to new environments, but it would prove that Earth is not unique in its basic structure. It would confirm that the galaxy produces habitable planets as part of its normal evolution. It would anchor the search for biology in measurable reality. Instead of asking whether habitable worlds exist, scientists would focus on how many, how different, and how far away they lie. As new observatories rise and new machines take shape, the search will continue with greater precision. They will reveal fainter atmospheres and colder climates. They will capture reflections from surfaces hidden in starlight. They will identify patterns that match the balance of chemistry and heat that defines long-term habitability. They will map the diversity of worlds that orbit stars across the galaxy. The night sky will look different once we confirm the first true Earth analogue. Each point of light will represent not only a star but also the possibility of oceans, clouds, and stable air. The idea that life may arise elsewhere will shift from speculation to expectation. The search will no longer point outward alone. It will reflect back on Earth and reveal how rare or common our conditions truly are. The story does not end with the discovery of Earth 2. It ends when we understand how many Earths the galaxy holds, and how many environments can sustain the delicate balance that allows complex chemistry to persist. This search has already reached across thousands of light years. It will reach farther still. Somewhere ahead is the first world that matches the stability of our own planet. When it appears in the data, the long journey of discovery will enter its next chapter. Have you ever wondered what would happen if a giant asteroid slammed into Earth? Prepare to be amazed by the sheer power of these cosmic collisions and discover the devastating impacts they've had on our planet throughout history. Did you know that a massive asteroid wiped out the dinosaurs millions of years ago? Explore the history of these catastrophic events and learn about the ongoing efforts to protect our planet from future asteroid threats. Imagine a world where the sky turns fiery red and the ground trembles with unimaginable force. This is the reality of an asteroid impact and will take you on a journey through history to uncover the devastating consequences of these celestial collisions. Welcome to Asteroid Impacts, the history of catastrophes. Today we're diving deep into the world of asteroids, those rocky wanderers of space that have shaped our planet in ways you might not expect. From ancient bombardments to modern-day defenses, we'll cover it all. So buckle up, because this is going to be an eye-opening ride. As someone who's always been fascinated by space since watching science fiction movies as a kid, I find these cosmic threats both terrifying and incredibly inspiring. They remind me how fragile our world is, yet how far we've come in understanding it. Let's start with the basics. What exactly are asteroids? Asteroids are rocky remnants left over from the early formation of our solar system about 4.6 billion years ago. Most of them orbit in the asteroid belt, a vast region between Mars and Jupiter, but some venture closer to us as near-Earth objects. These are the ones we need to watch out for, chunks of rock and metal that can range from the size of a car to several kilometers across, composed primarily of silicates metals like iron and nickel, or even icy materials. In some cases, asteroids vary in shape, from irregular boulders to more spherical forms due to their low gravity. Their orbits can be influenced by gravitational pulls from planets, leading some to cross Earth's path in what we call Apollo or A10 groups, making them potentially hazardous if they come too close. Now imagine one of these space rocks hurtling toward Earth at speeds up to 72,000 kilometers per hour. When it hits, the energy released is mind-boggling. To put it in perspective, a 1 kilometer wide asteroid impact would unleash energy equivalent to 100,000 Hiroshima atomic bombs exploding at once. That's not just a big boom, it's a global catastrophe waiting to happen, with shockwaves rippling through the atmosphere, seismic activity, triggering earthquakes and atmospheric injection of dust leading to climate shifts. We can see the scars of these events all over our solar system. On Earth, impact craters like the Meteor crater in Arizona, a massive bowl 1.2 kilometers wide and 170 meters deep, tell tales of ancient collisions. Formed about 50,000 years ago, it's a stark reminder of what even a small asteroid can do with its raised rim and ejected material still visible today. Then there's the Vredefort crater in South Africa, the largest verified impact structure on Earth, stretching 300 kilometers across from an event 2 billion years ago, where the force was so immense it exposed deep crustal layers rich in gold deposits. But Earth isn't alone. Look at the Moon. Its surface is pockmarked with craters from billions of years of impacts preserved without erosion or atmosphere to hide them, like the massive South Pole Aitken Basin spanning 2,500 kilometers. Mars too has giants like Hellas Planitia, a basin over 2,000 kilometers wide formed by an ancient strike that reshaped the planet's hemisphere. These examples across planets show just how common and powerful asteroid impacts have been in shaping celestial bodies, influencing everything from surface geology to potential habitability. From my perspective, these cosmic scars make me appreciate how lucky we are that Earth has an atmosphere to erode most evidence. Otherwise, our planet might look as battered as the Moon. As we move forward, we'll explore how these impacts weren't just destructive. They played a role in Earth's early history. Let's travel back in time to the Hadean Aeon, named after Hades, the Greek god of the underworld, because this period was pure chaos. From about 4.6 billion to 4 billion years ago, Earth was a molten ball of rock, constantly bombarded by asteroids and comets in what's known as the Late Heavy Bombardment. These collisions weren't just random destruction. They helped shape our planet by melting and reforming the crust, creating basins that could hold early oceans. Scientists believe this intense pummeling delivered water and organic materials that may have kick-started the origin of life with cometary ice, providing hydrogen and carbon compounds essential for prebiotic chemistry. Imagine, without these cosmic deliveries, Earth might still be a barren rock, devoid of the complex ecosystems we know today. But the bombardment didn't stop there. Fast forward to 66 million years ago during the Cretaceous-Paleogene boundary, when the most famous asteroid impact changed everything. Enter the Chicxulub impactor, a massive asteroid or comet about 10 to 15 kilometers wide that slammed into what's now the Yucatan Peninsula in Mexico. The crater it left is over 180 kilometers across, buried under sediment, but visible through geophysical surveys with gravity anomalies revealing its ring structure. The effects were apocalyptic. Upon impact, it released energy equivalent to billions of atomic bombs, triggering massive firestorms that ignited forests worldwide. fueled by superheated ejecta raining down like fireballs. Gigantic tsunamis hundreds of meters high ravage coastlines across the Gulf of Mexico and beyond, depositing layers of iridium-rich clay globally as evidence. The ejected dust and debris created a global nuclear winter with sulfur aerosols from the impact site causing acid rain and prolonged darkness. Sunlight was blocked for months or even years, causing temperatures to plummet and photosynthesis to halt, starving plant life and collapsing food chains. This led to the mass extinction of about 75% of Earth species, including the non-avian dinosaurs, pterosaurs, and many marine reptiles. But from the ashes rose opportunity. Mammals, including our ancestors, diversified and took over the planet, evolving into the diverse forms we see today, from tiny shrews to massive whales. Personally, I find the Chicxulub event a powerful reminder of life's resilience. It wiped out giants like dinosaurs, but gave tiny mammals a chance, much like how unexpected challenges in our lives can lead to new beginnings. This wasn't the last of it. Even in more recent history, asteroids have reminded us of their power. Take the Tunguska event in 1908 over a remote area in Siberia, Russia. An asteroid estimated at 50 to 100 meters wide exploded in the atmosphere. An airburst that released energy equal to about 15 megatons of TNT, equivalent to 1,000 Hiroshima bombs. It flattened over 2,000 square kilometers of forest, knocking down 80 million trees in a radial pattern, but luckily no one was killed due to the area's isolation. Eyewitnesses reported a bright fireball brighter than the sun, and shock waves felt hundreds of kilometers away, even registering on barographs in Britain. Then in 2013, the Chelyabinsk meteor lit up the skies over Russia. This 20-meter-wide rock entered the atmosphere at 60,000 kilometers per hour, exploding with the force of 500 kilotons of TNT, 30 times the Hiroshima bomb. The shockwave shattered windows across a wide area, damaged buildings, and injured over 1,500 people, mostly from flying glass and debris. It was a wake-up call. Even small asteroids can cause real harm if they hit populated areas, prompting increased investment in detection systems worldwide. These events bridge the gap between ancient catastrophes and modern threats, showing that asteroid impacts are not just relics of the past. So what are we doing about them today? Let's dive into the cutting-edge world of asteroid tracking and planetary defense. Scientists around the globe are on constant watch for near-Earth objects, or NEOs, using advanced systems like NASA's Asteroid Terrestrial Impact Last Alert System, or ATLAS, which scans the skies nightly for potential threats with multiple telescopes in Hawaii and Chile. Ground-based telescopes like those at the Catalina Sky Survey in Arizona, and space-based ones such as the James Webb Space Telescope with its infrared capabilities, provide crucial data to refine orbits and assess risks. For instance, when a new asteroid is spotted, astronomers calculate its trajectory using precise measurements of position speed and gravitational influences from planets, often employing computer models to predict future paths over centuries. To classify these risks, we use the Torino scale, a 0 to 10 rating system developed by experts in 1999. 0 means no hazard. The object will miss Earth entirely or burn up harmlessly in the atmosphere. A rating of 1 indicates a very low chance of impact, warranting routine monitoring, while higher numbers signal increasing concern, with levels 4 to 7 requiring international attention. 10 would mean a certain collision capable of causing global catastrophe, potentially triggering climate change or mass extinction. Thankfully, no asteroid has ever reached above 8 on this scale for confirmed threats, though some like Apophis briefly hit level 4 before being downgraded. Take asteroid 2024 YR4 as a recent example. Discovered late last year, it initially raised alarms with a small chance of impacting Earth on December 22, 2032, but in March 2025, NASA's James Webb Space Telescope captured detailed images revealing it's about the size of a 15-story building, roughly 50 meters wide, Further analysis in June 2025 updated the odds: 0% chance of hitting Earth, but a 4.3% probability of impacting the Moon instead. This shows how ongoing observations can dramatically change our understanding and reduce panic, emphasizing the value of multi-telescope campaigns. But monitoring isn't enough. We need to act. Enter mitigation efforts like deflection techniques. NASA's Double Asteroid Redirection Test, or DART mission, launched in 2021 and impacted the moonlet Dimorphos in 2022, successfully altering its orbit by 32 minutes through kinetic impact. It proved we can nudge an asteroid off course if detected, early validating methods like spacecraft rams for future use. Early warning systems coordinated through the International Asteroid Warning Network involving over 30 countries give us years or decades to prepare, including public alerts and evacuation planning. Other missions focus on study and prevention. The OSIRIS-REx spacecraft visited asteroid Bennu, collecting samples returned to Earth in 2023, helping us understand NEO composition for better deflection strategies, such as using gravity tractors or nuclear options in extreme cases. These efforts highlight humanity's proactive stance against cosmic dangers, blending science with international cooperation. To give you a fuller picture of how dynamic asteroid tracking is, let's zoom in on some of the most recent close calls and discoveries as of mid-2025. These examples show just how active our skies are and why constant vigilance matters, with NASA cataloguing dozens of approaches each month. First up, asteroid 2025 AC, a small object estimated at 4.2 to 9.3 meters wide, about the size of a small car. It made its closest flyby on January 2nd, 2025, passing at a safe distance of 0.36478 lunar distances, or about 140,221 kilometers. Discovered just the day before by the Atlas telescope in Hawaii, it posed no immediate threat, but its uncertainty region was only plus or minus 4 kilometers, highlighting how quickly we can refine data for new discoveries. Then there's asteroid 2025 AB, roughly 10 to 22 meters across the size of a bus. It approached on January 3rd, 2025 at 0.39835 lunar distances, or 153,127 kilometers. Found by the Catalina Sky Survey, its uncertainty was plus or minus 56 kilometers, and it served as an early-year reminder of the steady stream of NEOs we track. Another one is asteroid 2025 AZ 317 to 39 meters wide, like a small house. On January 11th, 2025, it passed at 0.59372 lunar distances, or 228,226 kilometers, discovered by Atlas in Hawaii with an uncertainty of plus or minus 275 kilometers. It was one of several January events that kept astronomers busy. In mid-January, asteroid 2025 BD 10 to 23 meters approached on January 17th at 0.62580 lunar distances, or 240,561 kilometers. Detected by Atlas in South Africa, its uncertainty was plus or minus 131 kilometers, and it added to the growing list of small but observable NEOs. Asteroid 2025 BT 45.1 to 11 meters came even closer on January 20th at 0.31283 lunar distances, or 120,253 kilometers, discovered by Catalina Sky Survey with uncertainty plus or minus 277 kilometers. It's a prime example of how even tiny rocks can get relatively near. Moving to July, asteroid 2019, JM, estimated at a similar small size, made a very close pass on July 9th, 2025 at 0.042615 lunar distances. This one was notable for its proximity, underscoring the need for constant monitoring. Similarly, asteroid 2019 NW5 approached on the same day at 0.038919 lunar distances, another tight flyby that scientists use to gather valuable orbital data. Don't forget asteroid 2024 PT5, a small rock first spotted in August 2024. NASA is tracking it closely for its next close pass in January 2025 after it safely skimmed by earlier this year. This one orbits in a way that brings it back periodically, and it's considered a mini-moon candidate due to its temporary Earth-captured orbit, where gravitational forces briefly hold it like a second satellite before it escapes. These real-time examples illustrate the bustling nature of near-Earth space, with over a dozen significant approaches in the first half of 2025 alone, each contributing to our growing database of NEO behaviours. In my opinion, seeing how close these rocks get without hitting us is both relieving and a bit unnerving. It makes me grateful for the tech we have, but also wonder if we're investing enough in planetary defence to handle a real threat. As we look ahead, the future holds even more promise and challenges in dealing with asteroid impacts. While the odds of a major collision are low understanding, the possibility of future impacts is crucial for our survival. Scientists estimate that asteroids larger than 1 kilometre in diameter, the kind that could cause global devastation, strike Earth about once every 500,000 years based on crater records and orbital statistics. Smaller ones, however, pose more frequent risks. For example, objects around 50 to 100 meters wide capable of regional damage like the Tunguska event might hit every few thousand years, with airbursts occurring more often over oceans. In fact, close approaches happen regularly without incident dozens per year within lunar distance. Take asteroid 2025 GH as an example. Though details are limited, such events remind us that most NEOs miss us entirely, but each flyby refines our models. But with over 2,480 potentially hazardous asteroids known as of May 2025, vigilance is key. Ongoing cases like asteroid 2024 YR4, which as of July 2025 has 0% chance of impacting Earth, but a 4.3% probability of hitting the Moon on December 22, 2032, underscore the need for constant updates. NASA's latest analysis shows it's about 50 meters wide, and while the risk to Earth is none, it highlights how probabilities can evolve with more data and the importance of monitoring lunar impacts as well, since moon strikes could affect future bases or eject debris toward Earth. This is where space exploration plays a starring role. Missions aren't just about defense. They unlock asteroids' potential as resources. NASA's Psyche mission, launched in 2023, is en route to the metal-rich asteroid Psyche, arriving in 2029 to probe its core-like surface with spectrometers and magnetometers. By studying its composition, we could pave the way for mining rare metals like platinum and nickel in space, turning threats into opportunities for humanity's expansion beyond Earth. Imagine harvesting these materials to build space habitats or fuel deep space missions. Asteroids could be the key to our multiplanetary future, providing in situ resources to reduce launch costs from Earth. Other initiatives like the European Space Agency's Hera mission following up on DART will test deflection in detail by visiting Dimorphos in 2026 to measure the impact's effects up close with cameras and LiDAR quantifying momentum transfer for kinetic methods. And private companies such as Astroforge and Planetary Resources are developing technologies for asteroid prospecting, envisioning a future where we harvest water ice for fuel or precious materials for industry through robotic landers and spectrometric assays. These ventures not only reduce risks, but also open economic frontiers potentially worth trillions in untapped resources, though they raise questions about space law under the Outer Space Treaty. Equally important is building awareness and preparedness. Events like the Planetary Defense Conference, which in 2025 simulated a hypothetical impact scenario, discovered in June 2024, involving a fictional 300-meter asteroid, bring together experts from around the world to refine response strategies. These exercises test everything from detection chains to evacuation plans and communication protocols, ensuring governments and agencies can act swiftly in coordinated drills. Public engagement tools such as NASA's Eyes on Asteroids app let anyone track NEOs in real time with interactive 3D visualizations, fostering a global sense of shared responsibility, and even citizen science contributions via apps like Asteroid Zoo. Think about it. Just a few decades ago, we were blind to most NEOs, discovering them only by chance. Now, with surveys like Pan-STARRS in Hawaii scanning vast swaths of sky and the upcoming Vera C, Rubin Observatory in Chile set to detect millions more. Starting in 2026, we're cataloguing thousands more each year, using AI-driven algorithms to sift through data. This progress means we're better equipped than ever to predict and prevent impacts, with concepts like nuclear deflection or laser ablation in development for stubborn cases. But challenges remain: securing sustained funding for planetary defense amid budget constraints, forging international agreements on deflection missions to avoid geopolitical tensions, and addressing ethical questions about mining space rocks such as who owns celestial resources and how to prevent environmental harm in space. As we advance, collaboration will be essential to safeguard our world, perhaps through a dedicated UN office for asteroid affairs, or public-private partnerships to accelerate tech like the NEO Surveyor Infrared Telescope. From my own view as a content creator passionate about space, I believe turning asteroids from threats into resources isn't just smart science. It's our best shot at becoming a spacefaring civilization, but we need global unity to make it happen, without repeating Earth's resource wars. In wrapping up, let's recap the profound impact asteroids have had on our world. From the chaotic Hadean Eon, where relentless bombardments sculpted Earth's crust and possibly seeded the ingredients for life through volatile delivery, to the dramatic Chicxulub event that ended the reign of the dinosaurs and paved the way for mammals to thrive in new niches. Asteroids have been both destroyers and creators in our planet's history. More recent brushes like the Tunguska explosion with its atmospheric devastation and the Chelyabinsk meteor's urban shockwave serve as stark reminders that these threats persist, capable of causing localized havoc even in our modern era, and underscoring the need for global readiness. Today we're not helpless against them. Through sophisticated tracking systems like Atlas with its all-sky surveys and tools like the James Webb Space Telescope's precise astrometry, we monitor thousands of near-Earth objects with unprecedented precision, updating databases daily. The Torino scale helps us quantify risks, turning potential panic into informed action by categorizing threats for decision makers, and with groundbreaking missions like DART proving we can deflect asteroids through kinetic, means humanity has taken its first steps toward active planetary defense, building on that with follow-ups like Hera. Efforts like OSIRIS-REx not only study these rocks, but also reveal their value as resources, hinting at a future where we mine asteroids for metals and water to fuel space exploration, reducing our dependence on Earth's finite supplies. Looking to the horizon, the frequency of impacts, rare for civilization-ending ones but more common for smaller threats that could disrupt cities or economies, underscores the need for continued vigilance and investment. Space missions like Psyche will deepen our understanding of metallic asteroids, while international collaborations at conferences simulate scenarios to hone our responses, incorporating lessons from past events. Public tools and awareness campaigns empower everyone to play a part, transforming fear into preparedness through education and participation. Asteroid impacts have shaped our past, challenge our present, and inspire our future. By embracing science and exploration, we can mitigate these cosmic risks and even turn them into opportunities for growth, from resource utilization to advancing human presence in space. The universe is vast and unpredictable, but our ingenuity gives us the edge to face it head-on. Through creating this video, I've come to realize that knowledge isn't just power. It's our shield against the unknown, and sharing it with you all is what drives me to keep exploring these topics. So what do you think? Are we ready for the next close encounter? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit that notification bell for more deep dives into the wonders and dangers of space. Stay curious, stay informed, and remember, knowledge is our best defense against the stars. Thanks for watching Asteroid Impacts, the history of catastrophes. Until next time, keep looking up.